All right, so we can finally get started here. So very much a pleasure to have with us Roman Genov from University of Toronto. Roman has worked with us for many years. In fact, I knew him at Johns Hopkins, where I was a student then. Has been at the University of Toronto ever since afterwards, has been doing really great work at the interface between silicon and biology, neurobiology, very broadly speaking. And so today he'll give a chalk talk on his latest work on computational imaging. And then on Monday, we have a neuroengineering seminar where he tells us about the other side of his work, about interfacing interfacing silicon with biology for neural recording and closed loop simulation. So with that, let's get started, Sir Roman. Go for it.
Thank you, Gert. It's a pleasure to be here as always. We do go a long way with Gert back to Hopkins. I'm now in Toronto. Hopefully you can hear me and see me well if you are on Zoom. So I'm here to share with you some of the latest developments on a couple of fronts. This Friday morning, this is my talk on image sensors, and the more detailed description of it is the work we've done on image sensors that are fast and field-programmable, so that we could perform motion artifact-free and versatile imaging. That's the essence of it. So let me jump to the outline.
And I'll turn my audio off so you can turn your audio on.
You seem to be muted.
I think maybe we were hearing him from Gert's microphone.
Okay, shows unmuted, sound check.
Can you hear me now?
Да, слушаю.
Yes.
Okay, excellent. So hopefully you can hear me now. So I'm hoping to cover these 3 points today. So give you a bit of an introduction of what computational imaging is, and why is it that we feel it needs the best of both worlds. It needs the ability to do very fast exposure to tolerate motion, yet provide slow readouts to keep the output data rate low, maintain the SNR, and keep the volume of the data low as well. And the main part of the talk is the second item here, where I'll talk about the image sensors that we are working on. We call them coded exposure pixel, or CEP. This acronym will come around a few times today, so hopefully you will remember by the end of the lecture what it refers to, which indeed address that issue. They provide multiple exposure for a single readout, as many as thousands of exposures per readout per frame. For those of you who are circuit inclined, and my audience here in person is circuit inclined, so I will cover the circuit implementation for a couple of such image sensors. And the last item here focuses on various types of imaging applications. I have quite a few to show. I may not have time to show all of them, but the point here is to speak to the versatility of such image sensors, why we can use the same design for a number of applications to indeed demonstrate that they are can be used quite broadly. So let me start by saying that next generation image sensors are the eyes of future technologies. As we go in from one era to the next, as shown in the upper part of the slide here. So far, computational imaging, specifically computational photography, has been used very successfully in cell phones. So indeed, cell phone cameras today are very good. They're very low cost, yet very good. So what enables that is something called computational photography. It's an ability to provide an output image as a function of so-called computational imaging burst, where you take a number of images, for example, as shown here on the right-hand side, and produce an output image, a single image that has an improved quality, depending what your needs are. Yet, if you look at other applications, this approach mostly fails. Mostly fails because in other applications, many other applications, motion is much faster. Motion is seen, or the changing illumination rate is also higher. So if you look at autonomous vehicles, if you look at surveillance, robotics, augmented reality, all these applications require new capabilities. So I postulate here that future image sensors would require fast 2D or 3D imaging plus computation to go beyond just computational photography in cell phones. Just to give you a very brief introduction what computational imaging is and what some of its applications are, you can see on the slide. So computational imaging is a field of computer vision where you use various computational techniques such as optical, electronic, and other computation to provide an improvement in your imaging task. So some of the well-known applications here are HDR on the upper left, structured light for Face ID, Apple phones, some techniques used in autonomous vehicles, and things like even imaging black hole or astrophotography by Google. These are more well-known. Others are maybe not as well-known yet, but developing fast. You have cameras that can image without using conventional lens. You have imaging of clouds from a number of microsatellites, imaging veins through skin, compressed sensing, and things like non-line of sight imaging. These are all examples of computational imaging. Just to focus on the first three here, perhaps the most known examples. So HDR imaging, how do you get wide dynamic range today in your image? What you do is you go and take a number of shots in the burst, as shown here, with different exposure time, and then you combine the best segments of each into a single image to get something where you have objects in a dark room and in a bright background and a window both showing up well, right? Similarly, if you look at the second application here, Face ID, you project certain structured light. It means just it has certain patterns or certain geometric shapes in it. In this case, thousands of dots are projected to get the 3D features of an object, a face in this case, and reconstruct it in 3D. Or autonomous vehicles or self-driving cars, many cameras, still facing many challenges in terms of ability to perform computational imaging because of the speed of the vehicle, yet already employed. For example, in this case, there are 8 cameras. Let me formulate the problem that we're trying to solve based on some of this introduction. The problem we're trying to solve here is that there are 2 types of image sensors that exist, and none of them satisfy the need that we have. Conventional sensors, slow and flexible. High-speed sensors are costly, noisy, and power-hungry. Let me put this in a context here. So conventional image sensors would reside in the lower left-hand side corner in this plot. They would be certainly low cost and have a certain output rate, so let's say less than 300 frames per second, yet they are exposing at the same rate as they produce the output. So one or just a few exposures per output makes them not tolerant to motion artifacts and inflexible for various types of computational imaging that is required. So if you look at this example here, this is one example of a motion artifact known as ghosting. If you take 9 snapshots, 9 snapshots in a sequence, and you have a moving object, then you get 9 of those objects, and you have to remove all but one with expensive digital processing, for example. So you could address this issue with motion intolerance by using high-speed sensors that reside in the upper right corner of this plot. So they certainly provide many more exposures, let's say 30,000 exposures per second, so about 2 orders of magnitude or more faster. And that makes them flexible because you have all this data that is coming in and you can process it. However, it comes at the expense of very high output data rate, which makes the camera immediately very expensive. You have to handle that data, and all the digital hardware that follows the output comes at a hefty price tag here. So not only that, but they also prohibitively power hungry in many applications. You have all of those A to D converters, for example, that have to run at a very high rate. To maintain good SNR, the lighting requirements have to be very, very demanding, very bright light. And the output data volume is still there. You have to handle it. So you have to have all kinds of high data rate links and storage requirements that come with it. So our solution is so-called coded image sensors, or more specifically coded exposure pixel image sensors that address the limitations of the 2 main existing classes of image sensors. So they reside here in the upper left. And the key feature of them is that they provide fast exposure. So you can ensure that you have motion tolerance to a large degree. They would enable robust active imaging for a variety of computational applications. Some of the examples I showed you earlier. Yet they provide slow readout. Slow in this case, in this context, is a good thing, meaning that's a standard video rate, so you don't have to handle high video rate output. And also importantly, they're field programmable simply by changing their firmware, the codes of the pixels. The user in the field can actually deploy it in a particular application. So that's the proposition here, trying to go in the upper left-hand side corner. Let me now tell you how we do this. That brings me to the second part of my talk, where I'll explain in a bit more detail how we can do multiple exposures, get single readout, and reap all the benefits of this multiple exposure. So let me start by saying that there are different types of coded exposure imaging. On the left-hand side is an illustration of a simple 5x5 pixel array that does purely temporal coded exposure, meaning that all the pixels have the same exposure time, and then you can turn all the pixels on or off for sub-segments of a frame to get that type of functionality. So there's no spatial difference for all pixels. There are also image sensors that perform what's known as partial spatial temporal coding, where you have blocks of pixels, or clusters of pixels that are coded and enables you that type of selective pixel group exposure control. Yet the finest degree of coding comes when you do per pixel coding in each pixel. So each pixel has, we have access to control each pixel's exposure individually at a very fine temporal steps within one long exposure or one standard exposure. And that's the approach that we follow. There's been some optical ways of doing that, so using micromechanical parts like micromirrors and things like that. We do it fully electronically. So that's just a description of what coded exposure is without necessarily explaining why it's useful. But let me get there. So where could I use coded exposure imaging? This is just a couple of examples here of what has been done, but without using electronic per pixel coding. So this is using large benchtop systems with various types of micromirrors, for example. You could take a single shot and then decode it to to play a short video clip. That's one thing you could do, as shown on the left here. You could do things like imaging in 3D under strong ambient light. So here we have a bulb that's turned on, and this is the color map of the depth. And these are just some lines of structured light that enable this technique to work. So don't worry about the stripes there. But you can see here that generally bright light is a very strong interferer, making the problem of conventional 3D imaging very difficult to accomplish. Yet it could be easily done with coding. So indeed, how this field has progressed over the years, maybe over the decade or so, is by using larger optical setups. So some examples are shown here, including at Toronto and elsewhere. And the idea is simple. You have digital micromirror device up there, and then you project light. And then when the code is 1 for that pixel, you deliver light to the pixel. When the code is 0, however, you deflect the light. The light is lost, which is not ideal, yet you get the coding. And in this case, you either integrate the light or you ignore the light. So that's one way to do this. This would be using so-called single tap architecture, where you only have one storage node, one capacitor, or one well, where you selectively integrate into. Now, you can also do this electronically. And the idea is that you shift the complexity of all of that large system with lenses and micromirrors into the semiconductor. You would have a sensor, your photodiode, and you would either collect it on the tap, on the pink area at the top there, or you would drain it. So the photo-generated electron would be either drained or collected at the top. So it goes up or goes down. That's the sorting capability. So it's on-off type of capability. Some of this work was done. Some of the early work was done also at Hopkins by Ralph Etienne Cummings some years ago. We can also extend this to perhaps a better way to code, a way where the photo-generated charge, the signal, is not lost. And this is one of the key features of our designs. We use 2 or more buckets, 2 or more taps. And the code allows us to sort the charge into 2 storage nodes, 2 wells, without losing any signal. This is what's shown here. And no signal is lost this way. As you can see, we sort up or down. So another way to visualize this perhaps is to tell you that instead of having any of the external optics or any other devices, you simply perform this functionality. You enable coding per pixel, and you perform selective optimization. So here the blue square is referred to type 1 accumulating, the white square is referred to type 0 accumulating. So here we have a certain pattern, 2 lines crossing as the code for a 3x3 pixel array. Here we have 2 lines parallel. Here we have another 2 lines perpendicular to the previous one. You keep doing that for up to 1,000 times, in our case, per frame, and then you read out at the end. So you end up with the output rate that is standard video rate, yet you're performing selective exposures at a much higher rate, and that takes care of motion artifacts. So to sum up here, we have pixels that are coded individually, and we can do exposures at the frame of at a rate of 1,000 or even more exposures per frame. Yet we read out at a standard video rate, right? So that means lower power of the camera. You don't have to deal with a high data rate. The illumination doesn't have to be very bright. Your SNR is maintained. This sorting operation, by the way, using pinned layers, is done noise-free. There's no noise introduced when you sort this charge.
Sorry, why is there no noise in this process?
Because you don't have any. So this is a buried. This is not a surface. This is not a surface region. So it's so pin photodiode is not. Basically, you have a pool of electrons in the pin region, and you're just shifting it to one to another. So there is no reset noise or no switch related noise.
You still have the shot noise, but that you have to.
Short noise, yeah, I mean photon noise, right? That's there. Yes, absolutely. I'm just talking about the electronic noise.
Okay.
So there's no, if you sort of take this, this is an incoming Poisson process, right? Then split it into two buckets.
Mhm.
You don't add noise in any way to the two buckets, right?
Up to that point, no. The read noise comes right after when you're doing the read out.
Okay, so it has the same amount of additive noise as if I were to do like a single bucket long exposure.
Correct. Yes. That's the nature of it. There's it's a bit more involved than my simple explanation, but that's the statement I'm making here. And you have a low output data volume, as opposed to high frame rate cameras that would be reading out each time from the tap and introducing read noise in the signal path, right? That's the argument here. And this enables many computational imaging applications, both passive, meaning there's no illumination required. So for example, HDR, and active illumination, where you could combine this coding with coding of your light source, like a projector, and get additional benefits or additional capabilities. And I will describe a number of these examples shortly. So indeed, what we have is these coded exposure pixel image sensors that can run at 30,000 exposures per second as a programmable global shutter, basically. And so this allows for better, faster, and cheaper imaging. And in fact, this will be an all-in-one platform that can enable versatile imaging. And I will demonstrate to you HDR, 3D, depth-selective imaging. We've done high-speed imaging, multispectral imaging, and so forth, all using one camera, the same camera, simply reprogramming its firmware. We're currently in the 7th generation of our prototypes. So this slide here is a bit busy, but the point is to communicate that we can do lots of things, so it better be busy. And indeed, there are different applications that we have done and aiming to do more. The first 4 or 5 is what I will aim to show to you here. And just a word on the versatility. And by the way, we do have an intent to make this technology commercially viable, if not commercializable or commercialized. So you would, if you look at the conventional sensors, you would realize that they're actually quite compartmentalized. They target usually one or just a couple of applications or market segments. So they are application specific, you could say. Whereas we position our sensors as application agnostic. So the firmware can be reconfigured by the vendor. And you could even consider thinking of it as an FPGA of image sensors, where it's versatile enough to be deployable in different markets, for example, as shown here.
And Roman, you will make a connection to compressed sensing here?
Absolutely, yes. We maybe not in this talk, not as much in this talk, but it's a natural modality that we can do. We have not focused. Well, I actually have data from yesterday's experiments in the lab. I can play it for you afterwards. It's so trivial here that we actually try to do things that were either difficult to do or impossible to do otherwise. But yes, so one thing we could do is we can, for example, take a high-speed video by simply programming a small neighborhood of pixels with different exposure interval, non-overlapping, sequentially, and you get a lower resolution video that is very easily upsamplable to almost the same accuracy as the original. That's the idea. So just a word on where we are. So we've been at this for a number of years, roughly 7-8 years or so. We were part of a DARPA program for 4 years, up to 2 years ago. We're currently in the 7th generation, so 6th and 7th generation. So some of the results that I'm showing to you here would be from the 6th and going back to 4th and 2nd generation. And 7th is in testing. 7 gives us the VGA resolution. Where we're looking to go with this is going to 3D stacking. back to Krista's question, this will be a different fab, a different arrangement. The aim here is to be able to scale up to, say, HD resolution or beyond, while maintaining pixel size fairly small. So we are at 7 micron today. If we can play some tricks in 3D stacks, we'll probably shrink it down by a couple micron more, so that we can reuse the conventional cheap lenses that are available and used throughout without actually changing the camera form factor. So we're in early ages of design and planning for a couple of iterations here, where we would have just the photo detector chip and a lot of digital processing in the background. So, yeah. Now, circuits. For those of you, and most of you here, who are in that domain, they're actually fairly simple at first glance. Not so when you start really working with image sensor process and realize all kinds of issues that brings. So what's shown here is one type of a pixel that we call code memory pixel. We have a couple of different, very different versions of the pixel. This one is by far much easier to understand, so I start with it, even though this is an older one. So the block diagram tells you what steps we go through. We preload the code. So blue corresponds to blue and so forth on left and right. And we activate the code globally. So it's a kind of a global code, if you wish. And then based on the code value, we either accumulate on step 1 and step 2, and then we repeat until we're done with the frame. So capital N is a number of subframes, number of the sub-exposures. How it's done in the circuit domain. So this is not unlike a time of flight pixel, even though it functions very differently. You have 2 latches in the per pixel that are pipelined. So you load the first one in a row serial fashion. Let me show that how it's done. So you preload row by row the first latch there with your code. So code is a 1-bit binary value for the pixel. And then you, so this is what's shown up there. So you preload the pixel in that first blue latch. Then you shift from the first to the second latch globally, the entire image sensor. And you expose, so that global matrix of codes is immediately applied to the switches here. Okay? So I move to the next slide, that's what it's shown. So now the yellow is a decision-making point. Do I go up or do I go down, depending on the code? And if the code is, excuse me, 0, you follow the red path. If the code is 1, you follow the green path. And then so this is only shown for 1 frame, just a couple of pixels. So you do this for all of the subframes, and then you read out. And what the pixel would look like is something like this. This is our older 11 micropixel. You have info diode and digital circuitry on the right. So it's a fairly straightforward approach. There's some tricks, of course, how to design the pixel. And one challenge here is having PMOS in the pixel. PMOS really doesn't work well with pixel in general. So we've come up with another pixel architecture shown here, that we call data memory pixel, that shrinks the pixel by about 2.5 in area, so about 7 micron, and requires no NMOS, no PMOS in the pixel. NMOS only. The idea here is you first take a snapshot of your image, store it in a temporary storage point, and then you, in a row parallel fashion, sequentially provide the codes and sort it into 2 tabs after the exposure.
And so those, sorry. So you have NMOS multiplexer implemented additional selection of the code.
This is all NMOS. There's no
It's all
PMOS.
NMOS.
Right.
NMOS switches to this.
Yes. So there's ways to do it cleanly. There's no issues there. So
That's why I have code and code bar. Right?
correct. Yes. So to shine some light on it, at least some foundries don't actually even support PMOS in the Pixel. So we did it at our own risk, and we paid some price for it. Because that creates difficulties in arranging layers and optimal dopings for the best photosensitivity performance. So PMOS is really discouraged, if not forbidden. Now, one other point on the circuits before I move on to applications is the fact that in our latest image sensor, we've included two ways of quantizing data. And that's one of the slides that I wanted to perhaps even have some discussion or maybe hoping to get some of your ideas on as far as where else we can deploy and use this image sensor. So on one hand, we have this coding that is fully arbitrary. You can apply any code at any point for the pixel. On the other hand, we have these two ways to read out. This is the conventional way. You wait until the end of the frame, you read out two tabs as two images. This is an unconventional way, in addition to that, where we can monitor the tab at each of the subframes. So it's like think of it as a fast binary imager, so 30,000 frames per second binary imagers. So we can actually combine these two in interesting ways to get some additional performance benefits. One, straightforward way is to think of this as a monitor of when the well gets near full. Maybe switch the buckets or just stop integrating, stop integrating altogether on that pixel. So this is how we get high dynamic range functionality. But I feel there's much more that can be done with this type of versatility. So think of it as a very high speed image sensor. We still image flux. We're not going to necessarily to single photon regime, even though that is a possibility. And we have this ability to interrogate the tabs at a very high rate. And we can also read out at a higher depth, bit depth resolution, let's say 10 bits, at a more conventional video rate, let's say 30, 60, 120 frames per second.
If I can interpret this, so you have a delta sigma there on the left, which is an innovating analog digital converter. So in principle, since you're innovating anyway, might as well do the process of quantization, one-bit quantization, while you're integrating all the.
You're saying there is some synergy between how it's done here, how it's done there. Yeah, that's.
So rather than waiting till the end and then integrating delta sigma, you can actually have the integration be part of the process of coded imaging.
Correct. Yes. So I mean, naturally have a comparator here already. So why not deploy that comparator to speed out the bits? Right. We've also done some SAR work, SAR ADC work in our next chip. In fact, the one we're testing right now. Again, there is some synergy, not maybe to that extent that you just mentioned, but yes, that's how it was inspired. So it's basically reusing a comparator from that. And what we are focusing on now, and this is very new, is how we can make a very simple ADC. So something that between these two without any extra cost overhead by thinking of interesting ways to generate VRAM. Spend a lot of time on this, and maybe a paper will come out of this or not in the next few weeks. But I'm very open to maybe chat more about this and see, if there's any interest from users or perhaps circuit designers on what else we can do with this type of very elementary programmability. Each pixel exposure code is arbitrarily programmable at a very high rate, and we can interrogate pixel output at a very high rate as well. This is non-destructive, right? So you can continue integrating as you're doing. And by the way, this also scales beautifully to stacked image sensors where we don't need to run long lines for these types of circuits.
Quick question, right?
Yes.
Sorry, I understand. So this one bit output per tab is what, for
ADC2, yes?
yeah. So this is like you said your code, which is like 39,000 quotes per second or something.
Right.
You're saying for each one of those.
Correct.
You can also tell me like a binary, like
Correct. Very quick.
value is either above or below some threshold.
Yeah.
Set.
So this is fairly low cost. It's just a comparator.
Yeah.
You can evaluate the current tap value for each code or every other code over there.
You say you get that in addition to the,
Correct.
so you have
Both. We use both, as I will show you shortly. I just want to ask Gerd on how much time I have. I think I'm 32 minutes in. We started a bit late. Is that okay? Okay.
Whoever needs to leave, they can leave. It's recorded. Always.
All right. So this brings me to this last part, where hopefully this, fairly high-level description of what we do, you will be persuaded that it allows for a lot of versatility in terms of the applications. So I will aim to show 4 or 5 on this chart that I showed to you earlier, the same chart. So let me start with some of the recent work, which is, this was a VLSI symposium a few months ago. Rahul Gulwit, who is the lead author of this, presented that work, and he's done, so this is basically from his slides, from his work. So if you look at the high dynamic range scenes, this is one scene with a partition in between, halfway through the vertically. So on the left is a bright object, on the right is a dark object. Either you overexpose on the left or you underexpose on the right. This is if you take use conventional camera and take the 2 snapshots of the scene with different exposure. Long exposure at the top, short exposure on the bottom. So if we do it with our image sensor, here's what we do. We record the first subframe using this high-speed comparators to quickly estimate the flux, the illumination at each pixel. And then we use that as a code for the next subframe immediately. So the bright pixel would, let's say very bright, would stop integrating. The dark pixel would continue integrating. And we continue doing that. And you can start seeing the bulb filament on the left there. These are just some intermediate snapshots of the 1,000 subframes that we have. And you see how the masks, the codes, the binary codes that we upload to the pixels change as we go through. And what we do is we read out using the conventional ADC, the delta sigma ADC, to get what's left at the end of the frame, what's there in the text. But we have additional information about additional range hidden in these codes. So if we take these codes, we can compute the exposure time method based on the codes, because we know when we started and when we stopped integrating on each pixel. And now if I take one and basically divide it by the other, and we get the HDR image immediately. And what we get is we get the boost over the native image, native pixel dynamic range by a certain amount, which is a function of the number of the subframes. And specifically, so if I start with full frame integrating, so for very low light, so let's say 900 in this case, you get SNR plot as a function of your digital number. And then if you change the codes, so that sets a native dynamic range for a pixel. Let's say in this case 44 dB, whatever it happens to be for the given technology of that you choose, right? So it saturates at some point, and that's your native range. But then if you code, and you get all these other characteristics, and you can basically, by changing code, you can stay in a very high SNR range without any dip, right? There's no typical, typically have a dip there. And that adaptive coding is approximately equal to basically 20 log base 10 of the number of subframes. So about 60 dB, 57 measuring experimentally. So you get 44 and another 57 on top of that. So for the total of just over 100 dB, 101 dBs or so. It's not stated here. So this technique adds 60 dB dynamic range on top of any photodetector that you already have. You don't need to, design a fancy fab process that does multi-well or any other techniques or log scale. You use whatever you have. The native range would be increased by 60 dB or more if you can do more subframes per frame. Yes, that's what I was meaning to say. Total dynamic range is 101.5 dB. And the point here is to illustrate. You take the native and you add 60. So if your native is better, if it's 60 dB, and you get into 120 dB territory. And the SNR doesn't have a dip. You can stay basically the level of about 35 or so. So that's one application that we've recently done that allows you to do motion tolerant than HDR. So in this case, it's one frame. It's not 2 frames, it's not 7, it's not 12, as I showed it earlier, right? It's in one shot, which means if you have fast moving scene, this will adapt. It's a scene adaptive. Even if you have a motion within the frame, it will still adapt to some extent to the motion, to the subframe rate limit.
Well, I guess if Toby Delbert were here, he would argue, well, not quite, because you still have the fudge, right? In this, it is 30 milliseconds.
The
If
trace.
there's movement, you still see something, right? The trace.
Yeah, so if you apply brute force manner, I mean, we are as good as one frame, which is better than 2 frames or 10 frames, right? That's the improvement. So it's a single shot technique. But there are ways to combine it with maybe motion tracking or even some compressed sensing at the same time, right? So if you have a bright object, you can actually detect
Yes.
it at a subframe rate.
Yes, if you use your augmented technique where you have an ADC at every subframe.
Right.
Now, not if you just wait until the end and then over the accumulated
Correct.
exposure, then
Yes.
you convert
Yes.
then you can recover whatever thing happened.
Sure. Yeah. I mean, so event cameras is another domain. So are SPADs,
Yes.
another family of image sensors, and we certainly are looking to position ourselves within that context. No question about it. And I have a slide on this. Maybe if questions come up, I can talk about it. But just to go through the applications, the remaining applications, this is a simple way to do single shot multispectral imaging. What you see, so what's shown here is a scene, shoe, a sneaker, and what's shown on the right is a upsampled output of our camera that gives you the spectral information at these wavelengths, including near infrared, by the way, and reconstructed color. And so the way it's done is you have number of light sources. So this is a grayscale camera. There's no RGB filters on it. And you project these wavelengths. So you're going to get this information from the scene at these wavelengths. And what you do is you take a neighborhood of 2 by 2 pixels and program them to collect the photogenetic charge synchronously with when these LEDs are projected. And then you get an output that you then split up into different wavelengths and upsample, and you get this motion tolerant way of doing multispectral imaging. So fairly straightforward technique, but enabled by having pixel code capability.
So this active, it requires active source.
This requires as many LEDs or light sources as the wavelengths, but these are just point sources. Very simple. It was literally just a handmade board without much effort or cost. Another technique that I'd like to highlight here is something that I refer here to as depth selective imaging or depth gated imaging. Or there is another term that's been used that's called light curtains. Using these cameras and using basic ray optics, you can actually constrain your camera to image any arbitrary 3D volume only within that volume, but not outside. And you can dynamically program that volume. So this is simplified to simply depth. So you have a scene, have 3 points here, green, yellow, and red. We would like to determine or set the range between point depth A and B to be one range, in range, and anything else is outside of the range, as shown here on the left-hand side as well. And the idea is that by simply using ray optics, which puts the projector as a point in the scene and point on the camera in one plane, you can selectively program where you expose and how you project. So you project a line and you expose only in this range. So you only record from this range. You're going to get only the range between depth A and depth B. And these are some of the results. So a little bit dark here, but you can see that object. Yellow object is shown, but not the other ones. They're just shadows. Or the two other objects, but not the middle object. This is raw data from the camera, no post-processing whatsoever. So you can think of applications such as, first of all, privacy. You can do surveillance only up to a certain distance, but not beyond. It's a big issue in our society, at least. You could think of security or safety applications. You have manufacturing plants. You can constrain where alarm would go off if workers would walk into certain proximity to dangerous sites, and many other applications as well, which I will not dive into, but again, this is open for, we're looking for good uses for this. And a couple other applications that are maybe more conventional. So something called structured light imaging or 3D. I alluded to it earlier when I showed Face ID. This example here, we use lines. It's a sinusoidal patterns that are shifted by 90 degrees. 4 of them are projected, and then the camera is configured to have neighborhoods of 2 by 2 pixels. So not unlike Bayer filter RGB type of mosaic, except that here they are dynamically programmed by codes to integrate for one of the patterns, but not the others, or maybe a couple of patterns, like in this frame here, not that. Then you can reconstruct these all done within single frame, because you haven't read out any of them. You just basically spatially multiplex these results. And if you do that, then you would get, let's say you have a scene like this, and you get these 4 images that you read out from 4 pixels, you upsample them, and then very easily from that, using standard structured light techniques, you get your albedo, which is basically the reflectivity of the surface, and in this case, it's depth. So color map here corresponds to the depth of each of these objects. And you can do this dynamically, because our point is to try to show that this is motion tolerant. So you have an object that's running around, and this is basically very simple computation you do on your raw outputs to get your 3D map. Or you can do something more complex, such as shown here. So you have shadows. Of course, when you have shadows, you fail to reconstruct, but that's expected. Or we worked on a project with a couple of collaborators where, in fact, what they've done is they optimized the optimum patterns for projection for a given camera or even given type of scene. So you start with random codes on the projector, and then you do stochastic gradient descent to optimize for the mean disparity loss. So you see they start from random patterns over there, and you arrive to these types of codes, and they give you the best mean disparity loss. So there are ways to improve codes, at least on the projector side, possibly also on the camera side. And the last application before I wrap up here is another way to do 3D imaging, which gives you higher accuracy in depth, but it is not an absolute, it's a relative metric. So you need to compute surface normals, second item here. So how each point on the scene is oriented in 3D space. This is what photometric stereo imaging is about. And a similar idea, but here you have to have 4 LEDs which are spatially separated. So the angle of incidence, the more different it is, the better result you get. And similar idea, you do the Bayer type coding, multiplex in a single frame, spatially multiplex in a single frame, and then you get a result which would be normals map. This is an older, so our second generation of image sensor, so a bit lower resolution here. You can see that there's all kinds of flickering. That's where the here is. That's normal, because here is the texture is is fairly arbitrary. Then you see here normals would be in one orientation and almost opposite orientation on the other side. So this gives you a much more accurate depth, but not necessarily absolute. So if you combine the two, which can be done on the cameras, you get both absolute measure of depth and an improvement using normal maps. Given that I'm at 47 minutes in, I'm just going to show to you what we do for fun in Toronto. We just held, this was a couple of years ago, we held another one last week or so I don't have any picture yet. You know, thanks to all the students and in large part for this great work and for the results that I was able to share with you. And I'm happy to take any questions. Thanks for listening.
The guitar and chess and everything.
Yeah, that's right. Well, at least once a year we do that. At least once a year we do that.
One point, previously this is tailored towards application of fast-moving objects. What do you do for neural imaging? How can it be used in such scenario?
So we're actually quite open to explore that dimension. I've been looking for opportunities and applications of such cameras. So there's a newly emerging field of computational microscopy. I just came from a conference in LA a couple of days ago. There was quite a few talks on the subject there. For example, some cameras use coded apertures. These are fixed masks that are placed in front of a camera, and with proper reconstruction actually gives you a way to image without using a lens. I mentioned the flat cam earlier here. There are other techniques using diffusive membranes and things like that. So our cameras offer the programmable way of doing these types of techniques. I haven't explored it beyond the statement I'm making to you now, but we certainly are interested. And in fact, if there is any interest here or any synergy, we would be happy to talk about it. Our aim, in fact, is to make cameras available to community, scientific community. So the 7th generation of this sensor that I mentioned to you is been currently, which has VGA resolution, has been currently debugged, and the aim is to make them available on loan for joint work. And if there is interest or ideas or how we can deploy them, we certainly be interested in that. So there are two ways, just to wrap up the answer to the question, there are two ways to approach this. One could be the conventional kind of large benchtop form factor instruments that do coded imaging, and if as long as VGA resolution and a fairly good foundry photodiode is sufficient for that, that's fantastic. In fact, what computational imaging gives you, it gives you the ability to use fairly average performance, yet get pretty high-end imaging results. On the other end of the spectrum are these the flat cam type cameras that are basically contact image sensors or nearly contact image sensors. Maybe, I don't know how much money Gert has, but we could think of making it flexible and wrapping over certain structures, right, and having photosensitive regions everywhere. But that's a very kind of futuristic long-term project. But yes, there's been a DARPA program on this topic, and people have looked at imaging. But usually, the key point is that you have to induce fluorescence, unless you're doing, bioluminescence or any type of natural light generation without excitation. But once you talk about excitation, delivering the excitation light becomes an issue. You have to have tiny light sources spread out on your imager, or maybe other ways of guiding that light. So that's a challenge that everybody faces, right? Do you use excitation light, or do you do passive imaging? And some decisions would be made there. I think I've covered some of the points regarding your question.
And you give another seminar on Monday, right?
And I'm giving another seminar on Monday, which deals with, will not talk about imaging, but it will talk about neuromodulation and ways to deliver electric charge to neural networks in optimal ways, including in a closed loop with machine learning. So if these two talks can find some sort of a merging point, absolutely, I'm happy to chat about that.
Yeah, thank you for that. I'm curious about how you get these sub-images, because I think that these sensors getting 2 taps. So the final output will be like the 2 images.
Correct.
Because you turn the sensor always on, just to lead to different taps.
Very good.
But how do you get the like sub-images that you show me in single charge that you get like 3 by 4 images?
Yeah, so you can combine them together. So some things are immediately, like the depth gated example is immediately, your result is immediate. Show you this. Basically, raw image. You have 2 taps. One is responsible for this range, one is responsible for out of range. So this is raw, no processing. Some other techniques may require fairly simple post-processing, right? We're not talking about like deghosting, like removing 8 out of 9 dirts. That's very expensive computationally. But things like upsampling or computing albedo and depth, for example, those are fairly straightforward techniques that are used universally in computational imaging. So yes, there is a little bit of post-processing. You talked about HDR. I'm going to go back to that. Right. So really, in this example, we just use 1 tab. So just use one of the 2, and the other one is used. It is not needed. Right? There are ways to improve this beyond that with 2 taps, and we're looking at that. But the simple answer to your question is 1 is sufficient to get this type of result.
Okay. Yeah, I was going to ask if you thought about sort of like optical designs that might go with these kinds of code sensors.
Right. So very good point. It leads me to another bragging point. I'd like to take advantage of your question to make, which is one way to see our approaches here, our technology here is an enabling technology for many existing techniques that are at the benchtop stage. Let me go all the way back to things like this, right? So this is amazing work by a number of groups in the computational imaging world. Some are quite recent, and more is happening. And they really mostly have a large jig like this, which is expensive and bulky, and that's still not optimum. One reason is because alignment of light source and the camera becomes prohibitively difficult. There are even some commercialization efforts on some of these from some of these projects, and very difficult to get things to align well. So if you had, why is that? Because you have to have 2 lines that are very closely matched to be, say, in the same plane. Whereas in our case, the alignment is not an issue at all. Any alignment will do. You just have to calibrate for, it's just a programmable line. So most of these techniques use basically raw scanners, rastering image sensors. So the best code they can do is 1 line. Whereas if you have an arbitrary code, then you can have a tilted line, for example. Moreover, all of these require large lenses, and really narrow field of view is a constraint because of aberrations. But what we can do, we have actually techniques to do that. We could, if we need to counter that, we can include distortion of the lens into our code. So if it needs to be a line that includes lens distortion, we just program it as such. We've done some designs, I'm not showing in this talk, where we have a digital coprocessor based on RISC-V and some other accelerators that actually do this type of code computation on the chip. So I don't have to run it somewhere on the computer and then ship it to the chip for each subframe. So it's done locally at the bottom wafer. But yes, so to answer your question, the idea is to make these fairly enabling or fairly versatile, because they solve all kinds of problems that comes with conventional optics, and not able to, lack of ability to provide arbitrary coding, for example, distortion compensation.
Yeah, I worked with rolling shutter in the past.
Okay, there you go.
Which is useful. But this is like obviously much better than rolling shutter on rolling coding.
Yes, so yes, we position ourselves as enabling in the sense that it solves all the problems, many of the problems that have to do with rolling shadow type of conventional sensors that are subject to these limitations.
So, like, I have a question on like the limitation on like how fast you can reprogram and like the maximum resolution it can do with this camera. So, is there since like the arbitrary coding like you have to do this row by row like within the pixel array. So, like, what's the distance that you like running?
Sure. Let me make it maybe a bit more of a high-level question. Rephrase it, and I can be more specific a bit later. So perhaps a question could be, what are the drawbacks or what are the constraints in this approach? So from a top level, we are replacing the need to ship a lot of digital video and quantize it and process and store it by having to ship lots of digital binary codes the other way to the chip. And the question becomes, is it really, is it really better, or does this advantage, is this advantage worth given that extra cost? And I think the answer is can be easily stated that indeed it is better. So for our case, for each subframe, you need to ship a binary matrix. So if you have 1,000 subframes, you need to ship 1,000 binary images, as opposed to reading out 1,000 10-bit images. So it's an order of magnitude or more improvement there. Second, most applications don't require arbitrary masks, so you don't have to ship these matrices, right? They're often just a 2x2 pixel tiles that need to be repeated. So there are ways to simply generate them on the chip or on the second wafer, and that bandwidth, the data rate is much reduced already, or lines generation, or shifting lines, or tilted lines, things like that. So we have done one design, working on next design of a digital coprocessor that can be programmed to locally, without having to go to DRAM, generate these types of special patterns.
In fact, yes, you can do sums of other products.
Yeah, ask about like already.
Yes. So we thought of some of those techniques. And as far as what limits the speed of the frame rate, so there are a few parameters here. Some are fundamental physical constraints and some are not. So the fundamental physical constraint really would be how fast you can shift the charge in this pin photodiode type of device. This is very technology specific, so it's none of our fits. So I can answer this way, that there are time of flight image sensors today that can modulate at megahertz or tens of megahertz, and if we use that pixel, we get the same benefit. The second constraint, also physics-based, is the comparator speed if you're using the binary readout. So you have to design a comparator that can offer you the ability to read out at the rate that matches your charge sorting or modulation rate. The third constraint, that's not physics-based per se, but it is physics plus cost, and that is how fast you can read out things. So there you have to have SerDes and number of channels, and how much of the data is processed locally on a coprocessor, how much of it is shipped on the high capacitance output lines. So these are the considerations. We'd like to be always limited just by the charge sorting time, and then all the rest is a design effort.
Yeah, sort of along that vein, for a lot of applications, a fixed pseudo-random code might be good enough, and you could design everything around that.
Correct.
And so if you could be in that regime where you're just limited by the charge sorting, if you're not shipping the binary code.
Yeah.
How fast do you need to go? Like effective? Yes. If I think of one subframe as a full frame, then I'm going to recover somehow.
So currently, I think all the other constraints removed. I think we'll go in single megahertz if we don't have to upload codes everywhere. We do have pseudo-random generator digital processor, but would generate codes on a separate chip that is envisioned to be stacked together in future designs. So we thought of ways of saving the cost of energy and processing time of shipping if we don't have to ship the code, why if we can generate the code locally, why do we have to ship it? Yeah, so that's a very good point. That'd be really interesting. But ultimately, this technology would really shine if it's implemented. This pixel design, pixel architecture would really shine if it's implemented in a time-of-flight type of image sensor process. We are not using that at the moment, but that option exists. So it's just porting it to the right vendor's fab to do this, and all of this can run at the same rate as time-of-flight.
Spout detectors? Spout?
No. So using charge demodulators, continuous wave. So this is indirect time-of-flight, not direct time-of-flight.
Is the processing like from the sub exposures to reconstructing like the final frames, the SDR frames, and the depth maps you're showing, like is the processing happening locally or?
Locally?
Yeah.
No. So on the output pipeline, on the output image processing pipeline, we're not doing it on chip. We don't have that. Usually, it's a separate processor anyway, but it's a fairly straightforward way. I mean, you saw that it's just your binary outputs are immediately fed in as masks without any post-processing.
Oh, great questions. Any questions from the Zoom audience? Just unmute yourself and ask questions.
Still digesting.
Hi, Roman. This is Abraham. I saw your demo in 2019 at ISSCC, and I thought it was a great demo.
Thank you.
I'm sure now the demo is even better now. I don't know if you've been doing demos during COVID, but how has the technology advanced since then for the 3D imaging with structured light?
Right. So thanks for remembering that. Back then in 2019, this was our second generation of image sensors. We are now in the 6th and the 7th. We've improved dramatically, I should say. We've improved. So back then we only had 4 subframes per second running. We could do more, but at the time it was the experimental limit. Now we have 1,000. So we've gone, by a couple of orders of magnitude in that aspect. Much of it is due to number one, getting rid of PMOS transistors in the pixel that caused us all kinds of issues, and we had to do thermal imaging and really scrutinize the design, basically doing device physics experimentation of our own, which is usually a no for circuit design unless you're a device engineer. And number two, we redesigned the pixel, and we've done maybe 24 of different pixels. And one of them will hit a sweet spot where a certain potential barrier with certain, half a micron shift of some layer made it much faster. Even our provider, the fabrication provider, wasn't able to give us that type of performance, but we just hit the sweet spot by basically search and a little bit of educated guessing. And that's what made us, very comfortable with the current sensors. We solved all kinds of other issues like blooming and, certain other non-idealities that one would, encounter in some pixels. And so, yeah, I think we're in pretty good shape, at least for the technology we've been using so far. We are looking to shift to 3D stack image sensor process. There'll be new technology, new challenges, but it's, I think, a lot more established process. I hope that answers your question. Specifically to structured light, it means that you can basically project more patterns for the same motion speed and get more accuracy in depth.
Yes, thank you very much. Thank you very much. And as for the 3D stack, well, the flip chip stacking, more correctly, right? With 7 micrometer pixels, that's gotta be hard, right?
For 3D stacking?
Yes.
So there's a question. So we thought of ways of doing this. Yes. So depending on the technology, you could have the vias. So these are kind of front side connections of the two wafers for the backside illumination. Yeah. So if you put one or two of these contacts, and you're already pushing the limit at 7. But there are ways maybe to multiplex pixels and use some, there are ways to combine pixels for the same interconnect. That way you have, you amortize.
Very interesting idea.
So if you can amortize the spatial price, the cost of the size of the interconnect, then you can still go low. I think is where we're going.
Thank you, Roman. Thank you for answering my question.
Any more questions?
I do have a question if there's time. So I'm a bit out of technology, but you were mentioning that in order to do time of flight, you need some extras in the process. What would those be?
It's a secret sauce that I don't even have an answer for you. It's a highly optimized layer stack with more layers, and actually much higher cost than your conventional pin photodiode. But it does give you a boost in speed, a significant boost in speed. Again, specific to Foundry, even if I had the answer, I wouldn't be able to tell you because this is all under NDA. So
does that mean that you actually whatever is happening is actually increasing the speed of the photo generated electron hole pairs?
It reduces the collection, yeah. So there are no trapped charges, there are no local minima when you are doing shifting. The layers are optimized geometrically so that they can collect faster. The gradient are things like that, because it's just a gradient. For the die is to have a potential well gradient for the charge to quickly move forward. And I'm
Okay,
sure
okay, so what you already have in your process right now is you have intrinsic layers where you're actually generating your photo pairs in an intrinsic region already, right?
Yes. Yes. So we're not using time-of-flight process at the moment, but we have an option to do so in the future. And yes, it's basically shifting from a pin photodiode to pin layer. So from a pin photodiode to shielded pin photodiode. That's what we do in the latest process. And
okay.
that's critical.
For someone who's out of the game for a while, that's as good as an answer as I can process. Thanks.
Thank you for the question, Christoph. I appreciate it. I'm happy to chat with you if you have specific questions which I'm able to publicly maybe answer.
Yeah. Okay.
Okay, very good.
I will follow up.
Thanks so much, Roman.
Thanks for Thanks for attending the talk as well. Yes, that's right. I'm going to disconnect here now.